in your Algebra 2 mind, what notation did we use to show that we had an inverse function? Yeah, so when you have an inverse in terms of algebra, you use that f, your function, with a little -1. So that means that you have an inverse related to the original function. So in trig, we still use that little -1, but there's also a trig term that we can use for that as well. When you're finding inverses, there are going to be a couple different notations to go along with it. And you have to, trig is different than algebra because trig has angles. So when we're finding an inverse in trig, we're really finding the angle whose sine is x, whose cosine is x, whose tangent is x. So going back to the unit circle, if we're finding the angle, our problem would look something like this. So what angle has a sine value of 1/2? Does anybody remember what angle has a sine value of 1/2? So get that unit circle back pictured in your brain. Think about the 1/2, that's the y of the ordered pair. So the x would be the square root of 3/2. Kaylin? Yeah, 30 degrees, or as a radian, 30 degrees is pi/6. Nice job. So that's what we're really finding with inverses. So a solution to an inverse is the angle. So on the homework from yesterday, I think 1, 2, 3, 4, the fourth problem asked you to find the angle, and we used the inverse in the calculator to find the angle. So that really is like finding the opposite. Inverse is the opposite. So anytime you find the angle, you're really finding the inverse. So the way we write that, there's 4 different ways we can show that in trig. The first one uses a special term, and that's this term here, arc. So if you see arc sine x, or arc cosine x, or arc tangent x, the ARC, arc, is a way to say inverse with trig. So an inverse function in trig terms uses that ARC, and you'll see both of them. The other form that is used commonly, there's 4, but 2 of them are more common, would be to actually use that little -1. Except it's not with f of x because it's with the function sine, or it's with cosine, or it's with tangent, and it's going to be attached to the function. The third form isn't used as much, but it kind of goes off of the definition of finding an inverse. So if I told you, how do you find an inverse, or I asked, how do you find an inverse? What's the process of finding an inverse? What do you do to find an inverse? Julian?
Well, you have to replace switch to x and y.
Yeah, you switch x and y. So if I take this equation, but I'm going to place it in terms of y and x. So if we have the equation y equals sine x, an inverse is found by switching x and y. So you may see the equation written as x equals the sine of y. And that would be like saying my angle is equal to the sine of whatever 1/2 would be. And then the last one is the one that you've been using in the calculator. You've been using that inverse function in the calculator. You see the sine -1, tangent -1, cosine -1. So any of those cases are ways for us to say inverse. In algebra, there's one option, f -1 of x, or just switching x and y, and then we get y by itself again. But there's a couple different ways in trig that we can note it. So we're going to graph first, and then we'll try and do a couple problems, and then we'll graph the other 2 functions. But we're going to graph sine, just like we've graphed sine probably 100 times at this point. We've graphed sine a lot, and cosine. So in the graph below, we're just graphing basic sine, labeling the graph like we've labeled it before. So pi/2, I, 3pi/2, 2pi. See if you can just label the graph like we've labeled every other basic sine graph. So the goal is to take the sine function and to try and see where an inverse would be located, and then how to create the inverse graph using sine. And then after you have it labeled, where does the sine function start? 0. Sine starts at the sine sinusoidal axis, which is at 0. goes up to 1, down all the way to -1, and then back up at the starting point. So just a little refresher underneath. The first question says, what test must a function or a relation pass in order for it to be a function? What's the test called? Yeah, vertical line test. So a function must pass the vertical line test. And how does that work, Hannah?
If you draw vertical lines like on a graph, no one has more than 1 point.
Exactly. So you're drawing vertical lines on the graph. Each vertical line must only pass through the graph once. This is a function. We've called it a function all of trig. So sine is a function. It passes the vertical line test. The second question, what test must a function pass? So now that you said yes, it's a function, in order for it to have an inverse. Julia?
The horizontal line test.
And what does that do?
If you put the line horizontally, is it that like it can't touch more than 1 point?
Right. So we draw a line horizontally, and if it touches more than 1 point, then it doesn't have an inverse. So, Julia, does this graph have an inverse? Does it pass the horizontal line test? No, it doesn't. Because if I draw a line, it's going to cross through what we have graphed 4 times, but I know that graph goes on and on and on forever. So we have to do something special to the graph to force it to have an inverse. And I want you to think back to y equals x squared, because that is one of the basic graphs that Algebra 2 and Pre-Calc are built on. And if we have y equals x squared, we have a lovely parabola. Would a parabola pass the horizontal line test? Nope. Does anybody remember what we did to make the parabola pass the horizontal line test? We said, whoop, this part's gone. And we're going to look at the parabola when x is greater than or equal to 0. Or we erased the other part and we looked at the parabola at the left side of it when it would be less than or equal to 0. So we forced it to have an inverse. We're using its basic shape, but taking a piece of that shape so that it has an inverse, because now I have half of the shape and that part does have an inverse. So we're going to do the same thing with this graph. We're going to force it to have an inverse so that it passes the horizontal line test, and then we can continue to solve the problem. So like math people don't like when things don't have an answer. There's always an answer for everything in math. It's not like maybe it is, maybe it isn't, like that English class. There's a lot of different ways you can reason through things. So if I look at my graph and I start at 0, because that's where we start the unit circle at angle 0. And usually we continue on a graph to move forward. So if I start at 0 and I start moving forward, right now we're good to go, passing the horizontal line test. But if you start to turn down to go to pi, will the function pass the horizontal line test? No. So that means my graph cannot go past pi over 2. Because if it does, it no longer passes the horizontal line test. If I go in the other direction to still see where can this graph exist so that it still passes the horizontal line test, I can go down, and at negative pi over 2, after that point, again, it no longer passes the horizontal line test. So I can pick a piece of the graph, and that piece then passes the horizontal line test. So just like the parabola, we chose a piece of it, we're doing the same thing. That portion for the sine graph is from negative pi over 2 to positive pi over 2. So I'm going to erase the rest of my graph. You don't have to erase the rest of yours. So this would be the part of sine. has an inverse. Like over here, this is the portion of x squared, a quadratic, that has an inverse. None of it exists. The rest of it doesn't exist anymore. So yeah, it's a wave that goes on forever. Well, not if we want to find an inverse. So we're going to try and actually graph the inverse. And to graph the inverse, we need to get some points. And there are only 3 points that we're going to graph from our current graph. So if you look at your current graph, we have a point at negative pi over 2 and negative 1, because that's the first point. Anything beyond that, it no longer had an inverse. We have a point at 0, 0. And then we have a point at pi over 2 and positive 1. Those are 3 points on the graph. How could you use those 3 points to graph this function's inverse? Because that's what we're going to do in the next set. Can you remember?
So you just flip x and y.
Yeah, you just flip them. So now that I have the 3 points from the function, the inverse takes those 3 points and flips them. 0, 0, of course, doesn't flip. But what was x becomes y, what was y becomes x. And we're going to plot these points, except now my x values are the numbers negative 1, 0, and 1. So my x-axis is labeled with numerical values. The y-axis is now the angles, and I have a negative pi over 2. We've got 0, and then we have positive pi over 2. So the axes flip because you're switching x and y. So if we plot the 3 points that are up here, negative 1, negative pi over 2, 0, 0, positive 1, positive pi over 2. We're going to connect these. When we connect the points, if you look at the original graph, the part below the y-axis, the part above the x-axis, sorry, not y, it needs to be a reflection. So the original function and the inverse is a reflection of each other. So if I look at this curve below the x-axis, it's kind of like an inward curve. My inverse function has the opposite curve. So by definition, yes, you switch x and y, but graphically they should be reflections of each other. And then again, above, I should have the opposite curve. So this is our inverse function. It's the only part that exists. It doesn't go beyond this. There is no more to the graph. So it doesn't go above pi over 2, it doesn't go below pi over 2, it doesn't go past 1 and negative 1. So the questions underneath want you to get the domain of this function that you have graphed above. So that domain goes from negative 1 to 1. That's the graph or the domain of our current function that we have pictured, the inverse. Ashley, what's the range of the function that we have pictured up here? Yeah, negative pi over 2 to pi over 2. And then the other 2 questions say, what's the domain of the sign? Well, the domain of the sign that we're using is right here. So the domain of the sign that we're using is negative pi over 2 to pi over 2. Notice that the range and the domain switch. So the range of one is the domain of the other because we're switching x and y. And then the range of the original sign is negative 1 to 1. And again, the range of one is the domain of the other. Questions? So when we go to find inverses for this graph or for these functions, they can only exist between these 2 points, between these 2 x values, between the 2 y values. If you have an angle that's beyond it, it doesn't exist. So it really is a very small restricted area. So if you have an angle of 3 pi over 4, it's bigger than pi over 2, so it doesn't exist. So if you look at the questions, there are 3 on the next page. And this is what the good portion of your homework, it's problems 5 to 13, part A. All of 5 through 13, but only part A. But this is how your homework is going to be set up. So it's going to say, find the values for the following if possible, no calculator. So we're going to use that unit circle. But this is what it's going to look like. It says arc sine in parentheses negative 1/2. I'm going to put this equal to the angle because that's really what we're trying to find. Now, you don't have to do all of these, but the first question says, what should you think? And this is just to kind of get you to understand what we're really looking for. So when you see this notation, we are really thinking, what is the angle whose sine is -1/2? So an inverse function means you're finding the angle because that's the part we don't know. So what angle has a sine that's equal to -1/2? The second part is the part that you must do. You need to take this and write it as an equation. So if I'm writing it in an equation, I want to take it out of inverse form and place it back into regular trig form, which means I need to switch the y and the x. So as an equation, this now says the sine of the angle is equal to -1/2, which is pretty much what that sentence says above. The sine of some angle is equal to -1/2. We're finding the angle. The next part says think some more, and this is where you need to kind of think about where this angle is allowed to exist. And we just said that it has to be between -π/2 and +π/2. It has to go between these two values. There's nothing on the graph. Here's my first quadrant. Here's my fourth quadrant, going back to the unit circle. So you got to think two ways. We're thinking of what the picture looks like, but we have to go back to the unit circle because that's where the angles are. So in the unit circle, the second quadrant and the third quadrant don't exist anymore for the inverse sine. So between quadrants 1 and 4, where is sine negative? We'll start with that. Say again? 4. So we need an angle in the fourth quadrant because that's where the sine is negative. That angle has a sine value of -1/2. I know sine is the y. If your sine is -1/2, or if the y is -1/2, what's the x value? Ashley? Square root of 3/2. So Ashley, in the fourth quadrant, what angle has the ordered pair square root of 3/2 with -1/2?
330 degrees.
So 330 degrees, or say it the other way in radians.
11 pi/6.
So she's saying 11 pi/6. So the problem with 11 pi/6 is 11 pi/6 has to go through the second quadrant, through the third quadrant to get to the fourth quadrant. So those angles don't exist. Like it's like a black hole. You can't pass through it, you fall off, you don't exist. So instead, we need the angle that goes in the negative direction. So Ashley, you just told me 11 pi/6. In the negative direction, that would just be not -11 pi/6. Just -π/6. So if we have an ordered pair of square root of 3/2, 1/2, that's a pi/6 angle. So if I want that in the fourth quadrant, I need to make it -π/6. So that instead of it going up pi/6, it's going down pi/6. It can't pass pi/2. So if your angle's positive and it spins all the way around, it passes pi/2, but that doesn't exist. There's only one answer. There's not two, just one. This is only one place where sine is negative between the first and the fourth quadrant. So let's look at the next one. Same thing, just trying to get you to see a different example. Get another one in. So the sine -1, the inverse sine of the square root of 3/2. And again, what should you think? Well, we're trying to find the angle. Square root of 3/2. Something like that. You don't have to write those exact same words, but like we're trying to find an angle that has a sine value of the square root of 3/2. Can somebody write the equation that would go along with it? Asher?
Would be sine of some angle equal to square root of 3/2.
Yeah. So the sine of some angle is equal to the square root of 3/2. I'm gonna just draw a little diagram to remind you. Pi over 2, negative pi over 2. This part here doesn't exist. So it can either be in the first or the fourth quadrant. And Asher, if it's a positive sign, it's going to be in the first quadrant. So if that is the square root of 3 over 2, x has to be 1/2. What angle is associated with 1/2 in the square root of 3 over 2?
60 degrees or pi over 3.
Nice. So we said 60 or pi over 3. Again, it's one answer. There's no other answer because it only is less than pi over 2, less than negative pi over 2. It's got to go between those two numbers, bigger than negative pi over 2. So the last one on this page, the inverse sine of 2. So we're trying to find the angle whose sine is 2. What angle has a sine value of 2? And then write the equation, so just like we did above, the sine of some angle is equal to 2. So, what angle on the unit circle has a sine value equal to 2? Julia?
No, I don't know.
No? Asher?
Is there no angle that has
Why not?
because the limit is 1 or -1.
Yeah. That's undefined because sine only goes from -1 to 1. Sine doesn't go to 2. The graph that we just drew stopped at 1 and -1. So this number isn't in that restricted region. So there is not a solution. Somebody have the calculator out. Drew does. Drew, if you type in the inverse sine of 2, what does the calculator say?
Error.
Let's say error domain, domain error.
Yeah, error domain.
And that's referring to the fact that this is outside of that domain. Doesn't fit. So there can't be an answer. So your homework tonight, there's not going to be a lot of work. It's more of a thought process. But I need to see a little bit of work so I know you're not just copying the answers in the back. Rewrite the equation, draw a little diagram, do something. Write yourself a comment. But most of the homework is just like this, 5 to 13. And then there's some calculator problems like the one Drew just said for us. Except you'd put it a different number instead of 2. So we're going to go through and graph the other two functions so that we can kind of see how their inverses work. So we know what the restriction is. So the most important part for us to think about is the restriction of the values. So the fact that it goes from negative pi over 2 to pi over 2 for sine. It's the most important part that you need to remember. Because if an angle's outside there, it's not a solution. So on the back of that page, actually I guess it's the next page, see if you can graph a cosine function for me. So graph cosine, label it just like we labeled sine. Graph your cosine function. So cosine starts up high and it ends at that same point. And then the questions, there's two questions, still has to pass the vertical line test and the horizontal line test. So for it to be a function, it's the vertical line test. For it to have an inverse, it's the horizontal line test. So the restriction, that's the important part. What piece will make it have an inverse? So if you look at your graph, what can we limit the graph to so we have an inverse for this function? Haley? So she said negative pi to 0, which right here to here. In most cases, I would say yes, except we try as hard as we can to start at the center of the unit circle, and the unit circle usually starts with the angle of 0. So Kaylin, if I start at the angle of 0 and move forward through the graph, we would use the 0 to pi. And that's the same thing with this parabola. The parabola, we really did the same thing. We started at 0. So instead of starting on the left or the right, we started at the 0, kind of like the center of the graph. So starting at 0, moving forward from 0 to pi is where our inverse exists for cosine. So remember, this is cosine now. It's different than sine because the graph is different. So we're going to take those 3 points, starting at 0 and 1. Our second point is at pi over 2 and 0. And then the third point is at pi and negative 1. Flip your ordered pairs. See if you can graph the cosine's inverse. So when you go to label your new graph, the x-axis now has regular numbers on it. It's no longer angles. So the x-axis has the integers. The y-axis is where the angles go. So we get a 0, the pi over 2, and the pi all the way at the top. So an inverse has the opposite. Y and x switch, x and y switch. So plotting the points, one point is at 1, 0. A second point is at 0 and up to pi over 2. And then a third point is at negative 1 all the way up to pi. And again, when you connect it, it needs to be a reflection of the piece that we're looking at. So the curve needs to go in the opposite direction. So above the x-axis here, its curve needs to go the opposite way. So they need to be a reflection of each other. If I could reflect it, it needs to go the opposite curve. So it's still a decreasing curve. Both of them are decreasing. But it's going the opposite, so it's a reflection. So if we answer the questions below, Julianne, the domain of the function graphed above would be from?
-1 to +1.
Right. And that's where that question, the last question came in. The sine of 2 doesn't exist. It's not within that restriction. Julianne, how about the range?
0 to pi.
Perfect. 0 to pi. And then the domain that we used for cosine was 0 to pi. Remember, there's a direct relation. The domain and the range switch for the inverse and the regular function. And the range of cosine is -1 to 1, which is the domain of its inverse. So we're going to graph one more function. I got 3 of them. Lucky for you, we don't find inverses of reciprocal functions. Because a reciprocal function, you can flip it back into sine literally by taking the reciprocal. So we don't find the inverse of the cosecant. We would take the value for cosecant, make it sine, and then use that. So there's only 3 inverses. You don't have to worry about 6 of them. So the last one here, we're going to graph tangent. But we're going to graph tangent. It says to count the same way. We're going to count by pi over 4. And the reason I'm using pi over 4 is because to get that tangent point, the tangent value, we need a smaller number to work with. So So this is just going to go to pi. I need to switch the directions up there. What does tangent have that the other graphs don't have, Ashley? Asymptotes. Do you remember where they are? Yeah, negative pi over 2. Right, and I only have negative pi over 2 to pi over 2 up here, so we have a set of asymptotes. In between the asymptotes, what's in the center? The origin, yeah, that's where our intercept is, right at the origin. So x-intercept at the origin. And then I wanted you to draw pi over 4 because at pi over 4, tangent goes up to 1. Remember, that's how we get the stretch of the graph. On the other side, at negative pi over 4, tangent goes down to negative 1. Tangent is an increasing function. So 1 period for tangent is actually the inverse of tangent. So what we have drawn here, this is the exact restriction. So from negative pi over 2 to positive pi over 2, and actually that gets parentheses because there's asymptotes. So the first period of tangent is the inverse for tangent. So we don't have to do any extra for this. There's no limiting it because what we have graphed is the inverse. So I'm going to see if we can try and flip this and get a graph. I'm going to use this point here. So at negative pi over 4 and negative 1, just like we did for the other ones, there's a point at 0, 0. And then at positive pi over 4, we're up to positive 1. So those are the original points. Flip them for the inverse. And then I also added the halfway angles on the y-axis. So when we graph this, if the tangent graph has vertical asymptotes, what do you think the inverse graph has, Julian? Horizontal. So at negative pi over 2 and pi over 2, those vertical asymptotes are now horizontal. So we're going to have horizontal asymptotes because your x and your y switch. So if it was vertical and it switches, it becomes horizontal. And then you're going to plot the point. At negative 1, you're going down to negative pi over 4. We're at 0, 0. And then at positive 1, we're going up to pi over 4. And your curve needs to do the opposite. So if you look at the curve that's above the x-axis, when you make your curve above the x-axis, it needs to curve the opposite direction. They need to be reflections of each other. In algebra, these two graphs are also inverses. You would have a cube and a cube root graph in algebra. So underneath, just one final time here, the domain of this function is negative infinity to positive infinity. Because a tangent graph goes on forever, so its inverse goes on forever. The range is from negative pi over 2 to positive pi over 2. That's where the asymptotes are. They get parentheses. So the domain of the regular tangent, again, exactly what we have listed for the range of its inverse. The range of the regular tangent is what we have listed for the domain of the inverse. So when you go to do your homework tonight, you need to know these restrictions. Tangent and sine are very similar, negative pi over 2 to pi over 2. Cosine is the one that goes from 0 to pi. You might need to refer to those 3 pages to kind of look at the restrictions. So the page I didn't get to would be the page where you're evaluating cosine. You do it the same way you would do sine. You're finding the angle whose cosine is the square root of 2 over 2, or the angle whose tangent is a value. So you're finding angles for your homework. Questions? A lot to take in for one day.
We